So how do you teach a new trick to a supercomputer when when the manufacturer has basically permanently locked you out of the code?
It sounds like a setup for a joke, but it's actually the biggest problem in AI right now.
Right. And today we're looking at this brilliant mathematical loophole that, well, it allows developers to basically hack the performance of the world's smartest AIs. Yeah. Entirely from the outside.
Yeah, it's a completely mind-blowing workaround.
So welcome to the deep dive. It is Thursday, June 18th, 2026, and we are unpacking this brand new state-of-the-art research paper from the team at Layer 6 AI.
Which they just presented at ICML 2026, by the way.
Exactly. And the paper is titled Agentic Monte Carlo, Simulating Reinforcement Learning for Black Box Agents, which, I mean, is a mouthful.
Oh, it's a massive mouthful, but the implications are huge.
Yeah, we have this thick stack of their research, their underlying data, all their testing benchmarks right in front of us. And our mission for you today is to really understand the mechanics of this impossible magic trick.
Because that's exactly what it feels like, magic.
We are going to explore how these researchers found a way to take the most powerful, securely locked AI models in the world and force them to learn highly specific, complex behaviors.
Yeah.
And they do it without ever touching the internal programming.
Right. And I mean, it fundamentally changes the landscape of AI development because this paper solves probably one of the most frustrating bottlenecks in how we actually build AI agents for the real world.
Which is what exactly, like what's the core bottleneck here?
Well, we have this massive gap right now between theoretical optimization.
Like how we know we mathematically should train an AI to achieve a goal.
Exactly. The gap between that theory and the reality of practical closed source systems. Because megacorporations simply do not allow us access to do it, and Agentic Monte Carlo bridges that gap entirely from the outside.
Okay, so to really grasp the magnitude of what Layer 6 AI pulled off here, I think we need to establish how much the landscape has shifted for you. We're not talking about large language models functioning as passive chatbots anymore, right?
No, not at all. The chatbot era is, I mean, it's old news.
Yeah, we aren't just asking them to write a sonnet or summarize a PDF. We are deploying them as agents.
Active agents.
Yeah. They're out there navigating cluttered e-commerce websites to find and purchase specific items, or they're writing software, executing that code, reading the error logs, and rewriting it.
Or conducting multi-step scientific research. I mean, they are taking continuous actions in environments where every single choice alters the future state of that environment.
Right, that's a whole different ballgame.
It is, because it means they have to plan 10, 20, or 50 steps ahead. And historically, if you want an agent to master a highly specific, complex environment like that, you rely on reinforcement learning.
Reinforcement learning. Okay, so we're talking about algorithms with names like proximal policy optimization, PPO.
Yeah, PPO.
Right.
Or the newer one, group relative policy optimization, GRPO.
But, and here is the massive catch, using PPO or GRPO requires a level of access that, well, normal developers just don't have anymore.
Right. Traditional reinforcement learning requires what the industry calls white box access. You need to be able to open up the AI's literal brain.
Meaning you're looking at its underlying mathematical weights, the billions of interconnected parameters.
Yes, exactly. You look at those weights and you compute policy gradients. You are literally rewiring its digital neurons.
So you're mathematically forcing the system to prefer a successful action over a failing action the next time it encounters a similar situation.
Precisely. You are actively changing how the model thinks on a structural level.
Which is kind of like a mechanic popping the hood of a sports car and physically tuning the engine, right?
Yeah, it's a great analogy. But the problem is, if you want to use the absolute smartest frontier models available today...
Models like GPT 5.1, Gemini 3, or Claude 4.6.
Right, those massive models. The manufacturer has welded the hood permanently shut. You cannot get in there.
You interact with them strictly through an API. You send a text prompt in, you get a text response out, that's it.
You cannot access the weights, let alone rewire them. And if we connect this to the bigger picture, that restriction has forced developers into a very, very frustrating corner.
Because if you want to build a highly specialized AI tool using these top-tier models, your options have been incredibly limited.
Yeah, you essentially have two bad choices. First, you could try endless prompt engineering.
Which is essentially just crossing your fingers and hoping you've written a clever enough instruction to guide the model through a 50-step task.
Exactly. It's totally fragile. Or The second option, you abandon the frontier models entirely. You download a much weaker open source model where you do have white box access.
Right, like an older llama model or something.
Yeah. And then you spend an absolute fortune on compute power trying to reinforcement. Learn it up to an acceptable standard.
But neither approach gives you the raw reasoning power of a GPT 5.1 that's actually optimized for your specific needs.
Exactly. You either get a smart model that's hard to steer or a dumb model that you can steer perfectly.
Okay, let's unpack this, because this is where the paper just completely blew my mind. If we absolutely cannot change the internal weights of the model,
Right. The hood is welded shut.
we can't rewire the neurons. So how do we mathematically optimize its behavior?
Well, the researchers at Layer 6 AI found a brilliant workaround. They tapped into this known duality in computer science. They realized that the goals of reinforcement learning can actually be reframed
Reframed as what?
as something called Bayesian inference.
Okay, Bayesian inference is one of those terms that immediately makes my eyes glaze over when I see it in a white paper.
No, I know. It sounds intense.
Yeah. How does that actually help us bypass the locked API?
So in Bayesian terms, you start with a prior. A prior is just your baseline intuition or the natural starting state of a system.
Okay, so the model's natural instincts out of the box.
Exactly. Instead of trying to open the black box and physically change the model's underlying nature, the Bayesian perspective says, let's just treat that natural instinct as a fixed prior.
Meaning we don't try to change its instinct at all.
Right. We don't change it. We just let the model sample a massive number of possible actions based on that instinct. And then we mathematically isolate the subset of actions that lead to the highest reward.
So we stop thinking like mechanics trying to tune a single engine, and we start thinking more like a sci-fi director managing parallel dimensions.
Yes, that is a much better way to visualize it. Because doing this perfectly across a 50-step task is computationally impossible.
Right, because there are simply too many branching possibilities.
Exactly. The tree of possibilities gets too massive. So to solve this, the researchers built the Agentic Monte Carlo framework around a technique called sequential importance resampling.
Okay, let me walk through how this looks in practice, because the mechanics are just wild. Picture a choose-your-own-adventure book.
Okay, I'm with you.
But instead of reading one path, our black box AI gets to play out 15 parallel universes at the exact same time.
Right, 15 simultaneous agents.
Yeah. And it takes one step forward in all 15 universes. Every few pages, the system basically hits pause. It looks across all 15 timelines, and it instantly deletes the universes where the AI made a terrible choice.
It just wipes them out.
But to maintain our 15 parallel paths, the system literally clones the universes where the AI is making good choices and lets the model continue branching out from those successful points.
You are stochastically pruning the dead branches and proliferating the healthy ones.
Stochastically pruning. I love that.
And the cloning mechanism is fascinating, too. You take the exact environmental state and the conversation history of the successful trajectory.
Right, the exact moment before things went well.
Yeah, you duplicate it in your system's memory, and you ask the black box API to predict the next step again. But you inject a slightly different random mathematical seed.
Oh, so the clone agent takes a slightly different approach moving forward.
Exactly. You steer an entire swarm of agents toward the optimal outcome, and you do it without ever once modifying the underlying language model.
It is literal survival of the fittest happening in real time across parallel dimensions.
It really is.
But, if you're listening to this, you've probably spotted the massive, glaring question mark in this whole setup.
The pruning mechanism.
Yeah. When we hit pause on the simulation, how does the system actually know which parallel universe is the healthy one?
That is the million-dollar question.
Right. Because if the AI is only on step 5 of a 50-step scientific experiment, how do we mathematically know if it's on the right track or about to ruin the whole thing?
That is the crux of the entire paper. Without an accurate way to score a trajectory mid-flight, Agentic Monte Carlo just collapses.
It would just be deleting universes randomly?
Exactly. So the researchers solved this by introducing a value function. It's essentially a tiny separate AI that acts as a judge or, well, timeline director.
Tiny director pruning the timelines. Okay, so what kind of model are they using for this? Do we need another massive GPT model?
No, not at all. They use much smaller open-weight models that developers can easily run locally.
Okay, so models like Llama 3.211b or Quinn 2.5.
Exactly. Those small, highly efficient models. They specifically train the smaller model to look at the agent's history up to that exact moment, analyze the current state of the environment, and output a scalar score.
A scalar score, so just a number.
Yes. That continuous numerical score predicts how likely this specific universe is to result in a final, ultimate success.
See, my immediate thought when reading that was, well, why do we even need to train the judge?
Right, because they are pre-trained.
Yeah. These open-weight models already have massive amounts of pre-trained knowledge. If the AI is trying to say buy a specific type of shoe on a website, couldn't we just prompt a stock llama model to say, hey, rate how good this search query is from 1 to 10?
It makes sense intuitively, and what's fascinating here is the researchers tested that exact assumption.
It did.
Yeah, they tried a zero-shot prompting approach, asking the pre-trained models to guess the value of a state based entirely on their general internet-scraped knowledge.
And how did it go?
It failed miserably.
Oh, really?
Oh yeah, it performed inconsistently and barely beat a random dice roll.
Wow. So general knowledge just isn't enough.
Exactly. The researchers proved that raw, pre-trained internet knowledge is completely insufficient for precise state value estimation in messy, complex environments.
So to accurately score a trajectory, the value function absolutely must be specifically trained on the actual messy data of the specific task.
It is non-negotiable. It has to be fine-tuned for the task.
Okay, but I have to challenge this setup, though, because the entire premise of Agentic Monte Carlo,
The parallel universes.
yeah, the whole reason we are spawning parallel universes and pruning timelines is because traditional reinforcement learning is too difficult, too expensive, and impossible on closed models.
Right.
But now, to make the parallel universes work, we have to go train a whole new AI model to act as a director.
I see where you're going.
Doesn't training that judge model require the exact same massive compute power we were trying to avoid in the first place?
It sounds like it should, right? But the computational difference is staggering.
How so?
Training this tiny director model is not reinforcement learning. It is a highly efficient offline regression task.
Okay, break down offline regression for me. How is that different from the RL we were trying to avoid?
Well, traditional reinforcement learning requires the model to learn while it is actively interacting with the environment.
Right, it's learning on the fly.
Exactly. It takes an action, calculates the gradient, updates its billions of weights, takes another action, and repeats.
That sounds incredibly heavy.
It is. It requires immense memory and compute to keep the environment and the massive model active simultaneously. But offline regression is entirely different.
Okay.
Think of it like studying game tape after a football match, rather than trying to learn the rules while actively getting tackled on the field.
Oh, okay, that makes perfect sense. So you aren't doing it live.
Right. You just run the black box agent a few times through the task, and you collect a static data set.
A data set of which moves eventually led to a win and which led to a loss.
Exactly. Then, entirely offline, you train the small judge model to fit a curve to that static data. You're just mapping specific environmental states to a final score.
And because the task is offline and the judge model is small, the resource requirements they drop off a cliff.
They completely plummet.
So how far off a cliff are we talking here? What kind of hardware did they actually use to run this?
The researchers ran all their Agentic Monte Carlo experiments, meaning training the tiny judge and running the live parallel universes on a standard workstation equipped with just 2 desktop GPUs.
Wait, 2 desktop GPUs?
Yep, 2 desktop GPUs.
That is the kind of rig a serious PC gamer or a bootstrapping startup has sitting under their desk.
Exactly. And compare that to the baseline test. To run the standard reinforcement learning algorithm, GRPO, on a similarly sized open source model, the researchers required a massive server node equipped with 8 A100 server GPUs.
Oh my gosh, the cost difference there is insane.
It really is. AMC gives you a statistically rigorous way to optimize behavior without needing to rent time on a supercomputer.
So we have this elegant theoretical framework. We use a tiny, computationally cheap director model to prune the branching timelines of a massive lock black box model.
Right.
But a director is only as good as the environment it's analyzing. If we throw this system into a chaotic, highly complex simulation, does the tiny judge actually know what a good move looks like?
It's a fair question. And to prove the resilience of the judge, the researchers deployed AMC inside the Agent Gym benchmark. They tested it across wildly different environments.
The scale of these environments is what really cemented this for me. Let's look at SciWorld, for example.
Oh, SciWorld is intense.
It is a text-based simulator for complex scientific experiments. The agent has to navigate a lab, gather materials, and synthesize chemicals.
And the environment allows for roughly 200,000 possible action-object combinations at any given step.
200,000. The branching complexity is astronomical.
It's a nightmare for a standard model.
So imagine the black box AI is trying to synthesize a compound. It generates 15 parallel universes. In universe A, the AI decides to pour water directly into a beaker of strong acid.
Which is a terrible idea.
Right. Before the AI even finishes the thought, the tiny director model, which was trained on past failures, instantly recognizes that specific state is going to result in a catastrophic explosion.
Right, it sees the disaster coming.
So it scores universe A as 0, immediately prunes that timeline, and replaces it by cloning universe B.
Universe B being the one where the AI is properly putting on safety goggles first.
Exactly. And it works across SciWorld and other environments like WebShop.
WebShop is great. That's where the AI has to navigate an Amazon-like interface with strict budgets and obscure item constraints.
Right. And AMC consistently and significantly beats standard prompting methods across the board.
The performance gains are undeniable, but the paper didn't just report the top scores, they ran ablation studies.
Tweaking the internal dials of the algorithm to see exactly what makes it tick.
Exactly. And what they found regarding the resampling rate is deeply, deeply counterintuitive.
Here's where it gets really interesting. If pausing the simulation to let the director kill bad universes and clone good ones is the secret sauce,
Which it is.
you would naturally assume that pausing more often would yield even better results. Like a hyper-vigilant micromanager making sure every single step is flawlessly executed.
Right, you'd think constant check-ins would be best. The researchers assumed the same thing.
So what happened?
They adjusted the resampling steps to test how frequently the tiny judge should intervene. The data unequivocally showed that intervening more often does not mean better performance.
In fact, it often destroys it.
It tanks it, yeah.
In the WebShop environment, they tested pausing the simulation 1, 2, 3, and 4 times to prune timelines.
Right.
The absolute best performance, the high success rate in buying the correct product, came from intervening exactly once,
Yeah.
right around step 6 of the process.
Just one intervention.
Yeah. When they cranked the dial up and intervened 4 times, the agent's performance tanked. Why does keeping a closer eye on the AI make it worse at shopping?
Because it mathematically proves the danger of micromanagement.
I love that. The math says micromanaging is bad.
It really does. Agentic Monte Carlo thrives on sparse, high-impact corrections at pivotal crossroads. If your tiny director intervenes too early or too often, it aggressively prunes timelines that might look slightly weird in the short term.
Oh, like a weird search query on the shop.
Exactly. It might look weird, but it actually contains a creative, highly effective solution in the long term. If an AI in WebShop tries a bizarre search term, a micromanager judge might kill that universe immediately because it doesn't look like a standard approach.
So you essentially choke off the diversity of your parallel universes.
You do. You have to let the AI wander and explore and only step in to prune the tree when a branch is definitively dead.
That is a fascinating psychological insight proven through computational math. But speaking of edge cases where the judge gets it wrong, we have to talk about the TextCraft anomaly.
Oh, yes, the TextCraft anomaly.
Because while AMC was crushing the benchmarks across the board, there was one specific test where, using this incredibly sophisticated parallel universe framework, actually lost to a completely dumb baseline.
The GPT 5.1 test on TextCraft. This is perhaps the most illuminating finding in the entire paper.
So they used the absolute smartest frontier model, GPT 5.1, to play TextCraft, which is essentially a Minecraft-style recipe-building game.
Right. You gather wood, craft planks, make a crafting table, that sort of thing.
It is relatively simple compared to the 200,000 combinations in SciWorld. But when they ran AMC with GPT 5.1, the tiny director actually made the model perform slightly worse than if they just run 15 random universes and blindly picked the highest scoring one at the very end.
The judge was actively sabotaging the AI.
How does that happen?
It happened because GPT 5.1 was simply too good at TextCraft.
Wait, if it's too good, shouldn't the judge just score everything at 10?
You have to remember how the tiny director learns. During that offline regression training, the judge needs to study the game tape. It needs to see clear examples of the agent succeeding and, crucially, clear examples of the agent failing miserably.
So it can learn to tell the difference.
Exactly. But GPT 5.1 is so advanced that it almost never made a catastrophic mistake in this relatively simple game. It produced short, highly confident, incredibly accurate trajectories every single time.
Oh, wow. So the training data for the judge was just endless tape of the AI doing everything perfectly. It never saw a failure.
Exactly. And this leads to a profound insight. Perfection breeds blindness.
Perfection breeds blindness. That's deep.
It's true. Because the judge never learned what a truly bad move looked like, it became hypersensitive to meaningless variations. When everything in the live simulation looks uniformly excellent, the judge struggles to differentiate.
So during the live resampling, it ended up hallucinating errors.
Yes. It accidentally pruned perfectly healthy timelines just because they used slightly different but equally valid crafting strategies.
So it tells us that Agentic Monte Carlo is a profoundly powerful tool, but it is most effective when the black box model is highly capable, yet still makes enough mistakes that external guidance actually adds value.
Right. If the oracle's already perfect, adding a tiny director just confuses the process.
That is a phenomenal takeaway. An AI judge cannot understand success if it has never witnessed failure.
Beautifully put.
So we've gone deep into the mechanics of Bayesian priors, offline regression, and the dangers of micromanagement. But if you are a developer listening to this or a startup founder trying to decide your tech stack, you might be thinking, running 15 models simultaneously through an API sounds like a nightmare for my server build.
It does sound incredibly expensive.
Right. Why does this highly technical ICML paper actually matter to the practical reality of building software today?
It matters because of the most critical constraint in the AI industry right now, cost and scaling.
Okay, let's talk numbers.
The researchers didn't just test performance, they did a rigorous analysis on the financial payoff of using AMC.
If they are running 15 parallel universes, how can they possibly save money? Let's look at the David versus Goliath setup they ran. They pitted a massive, ultra-expensive frontier model, GPT 5.1, against a much smaller, significantly cheaper black box model, GPT 4.1 mini.
And on its own, the mini model is highly capable for basic tasks. But it simply lacks the deep reasoning capacity to compete with the massive GPT 5.1 model on complex, multi-step environments.
But when they paired that cheaper mini model with the Agentic Monte Carlo framework using the tiny director to guide the mini model through 15 parallel universes, the math completely flipped.
It did. The heavily guided mini model suddenly matched, and in several complex reasoning benchmarks, actually beat the performance of the massive GPT 5.1 model.
And because the API calls for the mini model are fractions of a penny compared to the massive model, even when you factor in the cost of running 15 parallel trajectories at once, the final cost analysis is stunning.
Yeah, what was the final number there?
They reported at least a 50% cost reduction for inference.
50%.
You are extracting state-of-the-art, frontier-level reasoning on specialized tasks, but you are paying economy-class API prices to get it.
Which is huge for developers.
So what does this all mean? It means the researchers at Layer 6 AI have fundamentally proved that the AI community does not need to wait for mega corporations to open source their most powerful models.
Right. We don't need their permission.
By framing the problem through Bayesian inference and building this parallel universe architecture, developers can rigorously optimize locked black box AI agents entirely from the outside.
We can slash our compute costs in half, and we can force generic AI models to become highly specialized experts in incredibly chaotic environments.
We don't need the keys to the castle to train the king.
This raises an important question about the democratization of artificial intelligence.
How so?
Well, the trend in the industry is clear. The very best models will increasingly be locked behind opaque APIs for commercial and safety reasons.
That's definitely the direction we are heading.
And without techniques like AMC, independent developers and researchers risk being completely priced out of cutting-edge optimization. This framework is a lifeline.
It really is.
It ensures that the broader community still has a statistically sound, mathematically proven way to steer these massive systems without needing a billion-dollar data center of their own.
Which leaves us with a final thought to chew on as we wrap up. We started this deep dive talking about a massive black box oracle built by a mega corporation operating with billions of locked parameters that we aren't allowed to touch.
The welded-shut car hood.
Right. But Agentic Monte Carlo proves that if you build a tiny computationally cheap director model on a desktop computer and you use it to ruthlessly prune the timelines of that oracle, you can perfectly dictate exactly how that supercomputer behaves.
You're steering the giant from the outside.
Exactly.
Yeah.
So here's the question for you to ponder. If a massive locked superintelligence can be perfectly steered and controlled entirely from the outside by a tiny open source model.
Who is actually in control of the intelligence?
Exactly. The mega corporation that built the black box. Or you, the person directing the timelines.
That's a fascinating thought to leave on.
Thank you for joining us on this deep dive. Keep exploring the sources, and we will see you next time.